time to move on to classwork contemplations, the new stuff for today. Boy, we're going to do some hitting and running during this class. These are some topics that I'm sure you learned in high school, probably in middle school, and we just want to make sure that we go over them enough. The first of those topics is scientific notation, and we are going to go over, or I should say on your test, there are, I think there's one question on scientific notation. I don't think there's two. I think there's just one. So you got to be ready for it. So the big thing about scientific notation is this. It has to be a number between 1 and 10 times 10 to some power, okay? So for example, if you have 6 million or 6,700,000,000 and you want to express it in scientific notation, it is 6.7 times 10 to the ninth. Why is it 6.7? Because the format or the structure for scientific notation means you always begin with a number between 1 and 10. And if I made it 67 or 0.67, neither of those numbers is between 1 and 10. So by saying it has to be between 1 and 10, that gives me a uniform spot to always put the decimal after the first digit. Next, each time I move a place, it's a power of 10. So I move 1, 2, 3, then another 3 makes 6, and another 3 makes 9. So I've moved 9 total places, so the exponent or the power is 9. Another example, 0.00002. Well, I have to move that 5 places. 1, 2, 3, 4, the 4 zeros, plus the place of the 2, because if I stopped in front of the 2, I would have 0.2. I want to have the after the 2, so I have 2 point, and that's between 1 and 10. So it's 2.0 times 10 to the, in this case, negative 5. Why is it negative 5? Because it's 0 point. It's smaller than a 1. Whenever we have like 0.000 or a number point anything that's less than 1, the exponent is always a negative exponent on the 10. Next, 0.00037. Well, if I move the decimal to get to 3.7, which is between 1 and 10, 1, 2, 3, 4, that's 3.7 times 10 to the negative 4. And now I know it's going to be a positive exponent on this last one because I have a number bigger than 0. So moving my decimal point, which was after the 0, I go 3 places, 4, 5. So that's 5.79 times 10 to the 5th because I moved it 7 places. The 5.79 is between 1 and 10. So that's your basic scientific notation review. But why do we have this at all? Well, it all began in a land far, far away and a long time ago. A land where they make the very, very best food on the planet. A land called Italy. Now, it started with an Italian scientist by the name of Avogadro. What Avogadro's number is 6.02. Well, that's how I learned it in high school, 6.02. We didn't do the 214076 times 10 to the 23rd. Avogadro did not discover this number. It was named for him. He must have been a really important guy. Just by the look on his face at the corner of his eyes as he is in this picture, you know that this was a man not to be messed with. Avogadro's number is the number of particles in 1 mole of any substance. Mole having to do with molecule, and the molecules in a cubic meter at standard temperature and pressure. I haven't done that since I think I was in 11th grade. It's used to make very large numbers easier to handle, which it really truly does. The conversion between moles and grams depends on Avogadro's number. So basically, if you wanted to turn around and every single time you were to do a calculation and someone said, well, how many molecules are in this particular amount of volume? Would you really, really want to, by hand, multiply by 602-214-076-000-000-000-000-000-000-000. Would you really want to do that? That's insanity. It was just so much easier to work it with scientific notation. So Avogadro, being a mathematician, and mathematicians are two things. Mathematicians are brilliant, and mathematicians are lazy. He said, nah, I'm going to find a shortcut here. And he did. He created, someone created and named after him this particular number of 6.02 times 10 to the 23rd. And it allowed calculations to go much smoother in the days before calculators. So let's rewrite this statement using scientific notation. The coal extracted in the United States in 2005 produced 100, commas, 3 zeros, comma, 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 3 zeros, BTUs, British Thermal Units of energy. I have no idea how to say that number in its proper way, but I do know how to write it in scientific notation, and I hope you do too. Go ahead, give it a shot. Okay, so moving that decimal point, it begins at the end of the zeros. I'm going to move it 3, 6, 9, 12, 15, 18, 19, 20 places. So it is 1 times 10 to the 20th. That's 1 times 10 to the 20th is the number in scientific notation. 100 followed by all of those zeros is standard numeral form. Rewrite the numeral in the statement using scientific notation. The hard drive on my computer has a capacity of 12.0 gigabytes. Express your answer in bytes. Hint, giga means 1 billion. So you want to write this as a standard numeral. Go ahead. Okay, so if I write that as a standard numeral, 12 gigabytes would be 12 billion bytes, and that's 12 billion written out, okay? Remember, the first 3 places are the hundreds place, the next 3 places are the thousands places, the next 3 are the millions, and then we get into billions. So 12 is in the billions place, fill in zeros the rest of the way. Next, make an estimate of the following without the use of a calculator. Show your method, then do the exact calculation on a calculator and describe how well your approximation worked. 5 billion divided by 25,000. First, I would write out 5 billion. Go ahead. Okay, so there's my 5 billion. I'm going to divide it by 25,000. Now, here's the thing. You're going to do that on your calculator because nowadays we can do that on a calculator. But back in Avogadro's day, we just would have written it in scientific notation. I know I'm bald and I know I look old, but I'm not that old. They, in Avogadro's day, would have done it using scientific notation. 5 billion is 5 times 10 to the 9th. 25,000 is 2.5 times 10 to the 4th. So you divide coefficients and you subtract exponents. So 5 divided by 2.5 is 2, and 10 to the 9th over 10 to the 4th, subtracting exponents, is 10 to the 5th. So that tells me the answer. And then, of course, I would convert back. 2 times 10 to the 5th would be 2 followed by 5 zeros. If I do the calculator and I do 5 billion divided by 25,000, I also get 200,000. So either way arrives at the same solution. But you can see that before calculators, all right, you definitely, absolutely could do things much quicker using scientific notation, let alone Avogadro's number when you start getting into that big a number. Okay, giving meaning to numbers, perspective through scaling. And what we're talking about here is like with maps and to see how far apart something is and estimating travel times and so on and so forth. Again, a little bit of an archaic skill because nowadays when I want to know how far it is to get to someplace, I just go on to MapQuest and I write how far from one address to another address and it tells me. But back in the day when I had hair and I rode my pet dinosaur uphill both ways to school in the snow, in bare feet, we used maps. Verbally, I might say something like, hey, the map says 1 centimeter is equal to a kilometer. Graphically, we could put a picture of it like that. Okay, this is a centimeter here, and notice it's a kilometer, or 2 centimeters, 2 kilometers, and so on. As a ratio, 1 centimeter to 1 kilometer means a scale ratio of 1 to 100,000. Now, where is that coming from? I thought it was 1 to 1. Well, it's 1 centimeter to 1 kilometer. But how many centimeters are in a kilometer? There's 100,000 centimeters in a kilometer. So the actual scale ratio is that 1 centimeter on the map represents 100,000 centimeters in real life. Now, this is important because there's at least one, maybe two questions on your upcoming test that will ask you to make sure that you're able to make these conversions from like a kilometer to centimeters so that you keep the scale ratio in the same units, be it centimeters to centimeters, inches to inches, scale units like that. So, find the scale ratio for the following map. 2 inches on the map represents 2 miles on the ground. So this is a really good example of the kind of things you're going to be expected to do on the test. So give this a shot. Let's see how you do. Okay, so first I need to convert 2 miles to inches. That's the big change, because look, it's going to be choices on the map, or I should say the question is going to have choices. It's going to be choice A, B, C, and D. I promise you, none of the choices will say 2 inches is equal to 2 miles. That choice is not going to be there. There will be choices that say inches to inches, however, and that's the one that you're going to need to be able to convert to. So if I want to convert to miles to inches, it's big to small, so I'm going to multiply. Miles to feet, there's 5,280 feet in a mile, and there are 12 inches in a foot. So I take 1 inch times 5,200, or 1 mile times 5,280 feet in a mile times 12 inches in a foot, and I get 63,360 inches. So the scale is that 1 inch is equal to 63,360 inches. Okay? Find the scale ratio for the following map. 10 centimeters equals 10 kilometers. The centimeters is on the map, and the kilometers is actual. Go ahead. So, King Hector, or Henry, or whatever you want to say, King Hector died drinking deadly cough medicine. So I put in my 10 centimeters, and then I fill out to 100 till I get the 1 in the kilometers place, and that makes 100,000 centimeters. So 1 kilometer is 100,000 centimeters. All right, next up, the scale is 1 centimeter on the map is equal to 100,000 centimeters in real life. Okay, next up, according to modern astronomy, we're going to go through this together. Ready? I've got the whole solution written out for you. According to modern astronomy, the universe is about 14 billion years old. Suppose you represent this age with a timeline 100 meters long. What distance along the timeline represents 1 billion years, and written human history extends back about 10,000 years? How far would that be on the timeline? So first, let's do this with a little bit of scientific notation to make life easy. If you're 14 billion years old, then you're 14 times 10 to the 9th, which it looks to me like I only did 10 to the, I think I left off a set of zeros there. But, I'm setting up a proportion. 1.4 times 10 to the 7 years is to 1 meter. That's what we got here, okay? 1.4 times 10 to the 7 years is to 1 meter. As 1 billion years is to how many meters? I cross multiply, and I get 14 million times x is 14 million x is equal to 1 billion dividing by 14 million, and I get 71.4 meters. So what that tells you is that on the timeline, 71.4 meters is going to represent 1 billion years. Now it wants to know human history extends back about 10,000 years. How far would that be on the timeline? So again, the same scale, that 14 million years, or 1.4 times 10 to the 7th is 14 million. 14 million years is to 1 meter, as 10,000 years is to how many meters? It's called proportional reasoning. Cross multiply, 14 million x equals 10,000, dividing by 14 million, and I get 0.000714 meters. Okay. And the last thing I want to do on this particular video before I begin the next one is just remind you of rounding off real quick and easy. Everything about rounding begins with where the decimal point is. If I go to the left, I get the ones, tens, hundreds, and then thousands and so on. And if I go to the right, there is no oneths, right? After the decimal, you get tenths, hundredths, thousands, 10,000s, and so on and so forth. So the steps for rounding is to decide which decimal place you're looking for, and then you want to look one place to the right. For example, if you're rounding to the tenths, you look at the hundreds. If you're rounding to the hundreds, you look at the thousands and so on. If the next place is less than 5, you round down. If it's greater than 5, you round up. I think you're pretty good about that. That's like real basic, but I did want to make sure we hit it as a review. Several times on your test, you'll be called to round to the nearest tenth and so on. So that's it.